Good evening. I'm Harriet Hamasi. I'm University Librarian at Brown, and you're sitting in a room that has been open for less than a year. Last spring we had a series of talks, and they were so successful and really just so exciting that we decided to continue that tradition this year. And I just wanted to share with you a few things that will be happening, at least that we know will be happening in this lab as part of the series. So on October 17th, there will be a presentation by some folks from RISD as well as our own librarians talking about science, technology, engineering, art, and mathematics, sometimes using the acronym STEAM. Casey Dunn, who is a biology professor, will also be giving a talk October 24th at 5:30 p.m. Joe Gouldy, who is a new professor in humanities at Brown, actually in the history department, will be giving a lecture on October 21st, also at 5:30 p.m. John Caserta, who is a graphic designer who teaches at RISD, will be giving a talk November 14th at the 5:30 slot. And Butch Roven, who's the new chair of the music department, but whose own area of interest is electronic music, will be giving a talk December 5th. December 5th. So we hope that you will join us for more of these talks, but I'll tell you, we didn't save the best for the last. We put that at the beginning. Tonight we have a special treat. Dave Scott, I should say Commander David R. Scott, is the first guest for the series this fall, and we're just delighted that you're here to talk to us about Apollo 15. Over the years, Dave has been a true friend to Brown, and we've learned so much from you, and we so much appreciate that association. Jim Head is here tonight. Jim is a professor in planetary and geological sciences, and Dave and Jim have worked together for many years in both learning about the moon and other space explorations and training other students. And I'm sure you'll refer to that association as you talk tonight. The other thing that may be a surprise to you, I think it's a wonderful tribute. Dave was given an honorary degree in 2011 from Brown, an honorary doctorate degree. And he is also currently a visiting professor here at Brown in geological sciences. We just couldn't be more pleased and we're honored. Dave is most well known for being the 7th human to set foot on the moon, at least as far as we know. But prior to his career at NASA, he achieved a very distinguished academic background, including graduating 5th in his class from West Point, and also earning 2 degrees, 2 graduate degrees from MIT. It can be argued that Dave is one of the greatest pilots in the history of mankind. He flew 3 space missions, after all, and after completing the Apollo 15 mission, Dave received NASA's highest award for leading the most complex and carefully planned scientific expedition in the history of exploration. I mean, that's quite remarkable. So, even as government aspirations and funding models have changed since Dave's last mission to space, he personally has remained a dedicated advocate for the continuation of all forms of space exploration, including human missions to Mars. And I think you may talk about that a little bit tonight too. 2 things about Dave Scott have always stood out. One, he has a strong passion for exploring. And hand in hand with that exploration, the desire to explore, is the passion for learning. I think it's very fitting that his talk tonight is taking place in the Digital Scholarship Lab, because at its essence, the lab also supports and advocates for exploring and for learning. Please join me in welcoming Dave Scott.
thank you, Harriet. I appreciate that. Kind words. And I'm very pleased to be with you this evening. I think this is a great institution, and actually I learn more here than I give, because I've been working with Jim Head for 44 years, believe it or not. And I've learned an awful lot. It's great to learn, and it's great to be at Brown to learn. And so Harriet invited us tonight to talk a little bit about Apollo 15. And I've got a little PowerPoint. Everybody's got PowerPoint. I've got PowerPoint. But we'll walk through it. And at the end, we'll take advantage of the digital scholarship lab, because this is a spectacular way to visualize the visual images that we get from space. I'll go quickly through these slides and then be glad to entertain questions, as you will. But a little background, planning preparation, characteristics of the moon, Apollo 15, and within the context of Apollo 15 and Hadley-Apennine, I've highlighted science engineering synergism. And that's a key principle that we're working on at the present time. It's Jim's idea. He came up with it about a year ago, and we're working with MIT on the engineering side to bring the two disciplines together, because we found that during Apollo, this happened. We did this. We made the trade-offs. Scientists learned about engineering and vice versa. In fact, to sort of define the differences in a sense, some people would say science is what is, engineering is what will be. But if you look at it from an exploration point of view, when we went to the moon, why, the engineers were happiest when everything went exactly as planned. The scientists, on the other hand, were happiest when everything was a surprise. And we found a lot of surprises. So we sort of satisfied both sides of the equation. A little bit on Apollo and how we got to Apollo. Apollo was a space race for the Soviet Union, as you probably know. John F. Kennedy committed the country to go to the moon in 1961 within the decade, and we made it within the decade. And let me back up a little bit. One reason we made it was because of dedicated people satisfying a national goal. And it was a very simple goal. Man, moon, 1970. And everybody understood it. And that's something that we think the country should re-embark on, a goal, a destination, and bring everybody into the equation. I was lucky to fly on Gemini 8, Apollo 9, and Apollo 15. These images sort of show you the space race. The top was the USA, the bottom was the USSR. It was very, very close. And it's another longer story, but it was a close race. And for further reading, I was fortunate enough to become acquainted with Alexei Leonov, who was the first man to do a spacewalk, EVA. I met him some time ago, and he's quite a fellow, a very gregarious guy, but quite an adventurer in his own way. And so, yeah, about 2003, we got to know each other closely in terms of writing a book that somebody else suggested. And this particular book goes through the Cold War space race from my perspective and his perspective. It's sort of a parallel autobiography, and it's got a lot of little gems in there. His stories are a lot better than mine. My first flight was Gemini 8 with Neil Armstrong. First docking in space, second rendezvous in space. And it was sort of an exciting flight in that we had a little problem and had to come down early. Neil worked out a solution to the problem. But I thought I'd skim through some of this, some photos. The Titan II was our launch vehicle, and the upper center is the first picture I ever took in orbit of the airglow, and it is spectacular. It's a great scene. It's the horizon as the sun sets or sun rises. Upper right is the Agena target vehicle. The lower center is our first docking, worked like a charm, and then we had to land in the Pacific Ocean near the South China Sea and get recovered in the USS Gemini 8. A great spacecraft, but a lousy boat. I then got to fly Apollo 9 in March of '69 with Jim McDivitt and Rusty Schweikert. It was the first Earth orbit test flight of all mission hardware, software, and ops, except lunar operations and lunar landing. And again, I was fortunate to get to flight and get to fly with a great crew. A few pics from there. The first lunar module in orbit. I always tell McDivitt, he was flying it and I took the picture flying upside down. I mean, you know, it's supposed to be the other way, but if you look at the horizon, legs are up. On the right is Rusty Schweikert doing the first EVA in Apollo, testing the backpack, which was used on the moon. Lower left is the command and service module. Lower right is yours truly, hanging out the hatch on the command module because we were demonstrating an emergency transfer from the lunar module to the command module in case the docking tunnel was jammed. And I'd like to mention a little bit about the Apollo family. Few people know that during the peak of the Apollo program, there were 400,000 people working on the program. 400,000 totally dedicated people of all disciplines, science, engineering, technology, math, all of those good things. And it had a great culture, if you will, great philosophy. Everybody speaks up, everybody's heard, nobody's put down for anything. The managers make decisions and move on, and it really worked well. On the right is an example, or is a list of the contractors we had for the 400,000 people. Almost all of these now have been consolidated into 4 big contractors. But it was really a great experience. The configuration, as a comparison, in the lower right is a Mercury, the one-man spacecraft, and then above that on the right is the Gemini 2-man, and then we have the Apollo, the 3-man spacecraft, and comparisons of the launch vehicles on the left. Quite a lot of progress. But the real progress has come in the last 40 years. I always like to show this one because on the upper left is the onboard Apollo guidance computer, and it had 36,000 words, bits, bytes, whatever you want to do, convert it whichever way you want to convert it. Compared to today's, an iPhone has 64 billion or 32 billion, depending on how you are in the IT world and how you like to define these things, but billions more. The Apollo computer was pretty small at the time, but the software was absolutely brilliant. People who built it up at MIT in a Draper lab could make more things happen with fewer bits than anybody I ever heard of. And it really worked well. A little bit about the moon. One lunar day, as you probably know, is 14 Earth days. And the sun rises and the sun sets. And one of the key elements on the moon are the shadows. And the only thing that moves on the moon other than humans when they're there are the shadows. And they move about a little over 6 degrees per day. And in the blue there are the Earth days that we were on the moon and the shadows. On the right is the temperature. Gets pretty hot in the daytime, pretty cold in the nighttime. And one of the things a lot of people miss was we were on the moon for 3 days, 3 Earth days, but the sun never set. It was daylight the whole time. And a little adjustments had to be made. Some characteristics: no atmosphere, 1.6 G, very comfortable environment for living. Our lunar rover weighed 463 pounds on Earth, but only 77 pounds on the moon, which means we could pick it up and move it if it got stuck. Distances are difficult to resolve. You can't tell how far things are or how large they are. And I think the main reason is there's nothing to scale it. You know, on the Earth, all trees are about the same size. There are no trees on the moon, no telephone poles on the moon. So a problem we all had was looking at a boulder, is it a small boulder nearby or a large boulder at a great distance? And that was a real challenge. High temperature, Our pressure suits were superb, and they took care of us very well, and we never got too warm. Shadows, as I mentioned, the only motion, and dust. A real problem on the moon is the dust. I like to think looks like and feels like a combination between graphite and talcum powder. It's very, very fine and very pervasive. And when we got back, you know, our suits were really pretty dirty, good clean dirt, but very dirty. They've never been able to get them white again. They've never been able to take the gray out. And one of the problems with the dust, it gets in the connectors. And after about 3 days, we knew we were having problems. And one of the challenges in the future that hopefully somebody at Brown can solve, what do you do about the dust? To stay longer than 3 days, you're going to have a real problem. So on to Apollo 15, little PR up there. And one of the reasons is we had to land over some mountains. And I'll show you a little bit more about that. But we had to change the landing configuration to get into the site that was most desirable from a scientific point of view. We went to a region called the Hadley-Apennine, very difficult to get to, but because of NASA's capability in simulating and training us, we were very confident that we could get in over the mountains. There's our crew with all the things that we had to carry with us. In the yellow circle on the right is the geology tool rack that was on the back of the lunar rover. We had a lot to learn, took a long time, but again, we had great support, great simulators, and great training. Jim Irwin is on the left, Al Worden in the middle, and I'm on the right. And the NASA PR people gathered all this before we went just to sort of show what the mission was going to be. As you probably know, there were 6 lunar landings. Apollo 15 is in the upper center, 25 degrees north, at about, as we look from the moon, about 0 longitude, in the Apennine Mountains. And to put it in context of all the lunar landing missions, why Apollo 15 was the first of the J, the numerical designation, extended science missions. July 2671 had the first rover, and I'll summarize a lot of this, but the reason we were able to do what we were was because the previous missions started slowly, gradually, step by step, to improve the capabilities, and the big step was the scientific improvement of Apollo 15, 16, and 17. We launched on July 26, 71, Saturn V, right on time. Another sort of interesting aspect of Apollo is almost every flight launched exactly on time. And it was rather remarkable. With all of that, the total weight of the launch vehicle was 6 million pounds, and the total thrust was 7.5 million pounds on launch. Pretty spectacular ride, pretty rough, pretty noisy in the beginning, but very smooth as we got into orbit. Our target was the Hadley-Apennine. If you look at the man on the moon at night and the way you see it from the Earth normally, our landing site sort of on the inside corner of the right eye. In going to the moon, and I'll just briefly, at the bottom is a sort of departure. And as the moon moves around the Earth, why the lunar module and command module go into lunar orbit, and then they separate. Lunar module lands, command module stays in orbit, and then after the exploration on the surface, lunar module rendezvous with the command module, docks, and then heads for home. It's a 12-day mission, 3 days to the moon, 1 day in lunar orbit to get ready, 3 days on the surface, 2 days back in lunar orbit for science, and then 3 days to come home. There's our friend the moon, and there's a photo from lunar orbit. And I'll just quickly skim through these to give you an idea of the variety and the spectacular views in lunar orbit. The front side and the back side are very different from each other. In fact, when we went to the moon, having heard from our colleagues who'd been there before, normally in a procedural aspect, when a spacecraft gets in lunar orbit, first thing all the engineers want to do is check everything out, make sure it works. It takes a lot of time. So we scheduled to do minimum checkout. All three of us had cameras. We spent the first 2 hours going around the moon taking pictures, because it is a spectacular sight. And it's interesting to see from lunar orbit the color of the surface. It goes from some parts look white to a light gray to a dark gray, and then if you're in orbit looking up sun at the right angle, the surface of the moon is brown. It's chocolate brown. In fact, when the first flights got back, we had big debates about what's the color of the moon. Well, it's gray. No, it's brown. It's really amazing. Wrinkle ridges, they call them. We have a lot of terminology now for certain things, and this is where the lava is backed up against each other and solidified. There's the Aristarchus Plateau with what they call a cobra head or rille, and that's probably one of the more spectacular scenes on the moon. On the far side of the moon, there are no very big craters, only one big crater called Tsiolkovsky. And it too is spectacular in that the central peak is very bright gray, but the surrounding area before you get to the edge of the crater is dark black, black pool. And it's really quite a sight. Here's another little interesting characteristic of many. In the bottom, they call this the paper clip ridge. And it looks like a paper clip along some rills. But on to the landing. Our area, as I mentioned, was 25 degrees north on the edge of the Imbrium Basin in the Apennine Mountains. And you can see the little yellow spot was the area we went to. And you can see pretty much the scaling, about 20 kilometers from the edge of a rill to the mountains on the right. And that's our area again. On the right are the Apennine Mountains. They go up to 12,000 feet on the right and 9,000 feet on the left as we came down along this track. That was a pretty sporty course, but again, because of NASA's capability to analyze and simulate the approaches, why we were able to clear the mountains pretty well. Oop, oop. There's our landing site, Hadley Base, next to the Hadley Rille, which is about a mile across and 1,000 feet deep. One of our scientific objectives was to explore the rill and look at it to see if there's layering in the lava on the other side of the rill, because NASA had never seen layering on the moon, and the curiosity was, is there layering, or were these great flat lava areas just one big flow? There's Hadley Base, Jim Irwin, the flag, our lunar module Falcon, and Rover 1. We always like to have a little bit of showbiz when you get on the moon. I mean, you can't do all engineering and all science. You got to have a little fun once in a while. Sometimes you have too much fun, but anyway. There's the lunar rover, electrically powered, battery in the front lower part. On the right side of the front of the rover is a television camera, remotely controlled from the Earth, the first color TV from the moon, antenna to help guide the camera. There's a camera right in front of me. I'm holding on to the stick. The stick is how you drive the rover. You know, Jim and I were test pilots, so they wanted to make it simple for us to fly. So instead of a wheel, why, we had a stick, like an airplane. And if you want to go forward, you push it forward. That works. If you want to stop, you can't back it up, but you want to stop, you pull it back, the brakes go on. You want to go left, you tilt it left, right, tilt it right. Works like a charm. Independent power on each wheel, front wheel steering and rear wheel steering, so you can do a tight circle. On the rear is our geology tool rack. And as I mentioned, on the moon it weighs 77 pounds. And it was an amazing vehicle. I mean, it was brilliant engineering, and it enabled us not only to go great distances and carry a lot of tools and equipment, but bring back a lot of rocks. So it was quite an addition to the basic Apollo configuration. Now I'd like to run through a little bit on our science engineering synergism, because I think this is very important from an academic intellectual learning process, and especially today when systems tend to get very, very complex, and we know a lot about every discipline, to get this cross-fertilization and understanding is really important. And I'd like to show you how it worked during Apollo, because it worked very well, and we really didn't understand at the time what science engineering synergism, quote, quote, was, but we knew we had to work together and make these trade-offs. So I'll give you some examples, and I'll show you one of my favorites. This is sort of the timeline for Apollo 15. In the upper left, in November of '69, just after Apollo 12, and we were backup crew on 12, we were assigned, but we weren't announced, because NASA made the announcements from a PR point of view and from a probably budget point of view, so when the crews were announced, they were announced at a specific time. But in the meantime, we began our training, which was quite important because we had a lot to do. And if you look over on the right, there's the launch, the launch date, the landing date, and the return date. So soon after we were assigned, we had the opportunity to review the training plan. And in those days, the commander had quite a bit to say in terms of what the training was. And I'd had some geology training, some pretty good training on Apollo 12, but it seemed to me and a lot of other people that we needed more in terms of scientific training. On our backup crew was Jack Schmidt, Harrison Schmidt, who was a professional geologist. He was very influential in encouraging us to try to get more science time. So we had a training plan review. Right away, immediately I sat down with our training coordinator who coordinated and planned all of our training and said, let's look at what's laid out and let's see what we can do to enhance the science aspects of the mission. So one of the things they had us plan to do was to develop and test the toilet. Another thing they had us plan were 14 hours of microbiology. Now, 3 flights had come back from the moon. They'd all been quarantined, no bugs. So that was clean. So we thought, 14 hours of microbiology? So I sat down with our training coordinator and I went to my boss and I said, you know, can we do a little shifting here? Can we make a trade-off from engineering to science? Boss said, well, okay. So we scrubbed those and we did increased geology training. And if you look at the field trips, which are in green, before we went, hardly any. Then as soon as we got assigned, we put in a lot of field trips. And we made a lot, and it was very beneficial from the exploration point of view. So once that sort of worked, about April of 1970, the mission was changed from an H, that is in July, to a J, the extended scientific exploration. So then we started really rolling in the science perspective, especially since we got the lunar rover. So if you look at the second set there, mission went from H to J. So the lunar module was upgraded. We got a lunar roving vehicle, and they put a big scientific instrument module in the command module for lunar orbital science. Proved that, so we increased the mission to 3 days, traverses, increased the payload mass, and moved on to other trade-offs. Hadley-Apennine was one of the candidates for landing, and there was a great deal of controversy because we had to increase the landing trajectory from 12 degrees angle to 25 degrees to get over the mountains. And so we ran a lot of simulations. We talked to the engineering guys a lot to see if we could get over the mountains, and the answer was yes, you can. Went to management. Management awarded us really Hadley-Apennine. And one of the key points of that decision was a memorandum written by a young geologist who worked for Belcom at the time. Turned out to be a fellow named Jim Head. And I still have his memo because he wrote a spectacular memo on why we go to Hadley. And that one won. Now I'd like to talk about one trade-off in particular. When we looked at our simulations, we realized that the normal process of rendezvousing around the moon was to do 2 orbits, to get one to set up and one to come around and dock with a command module. We ran a lot of simulations, and based on early Jim and I work, we realized we could launch directly from the moon and in a half orbit get to the command module and dock, which saved a lot of propellant. And we went to the Mission Techniques Committee and presented that, and turns out that the head of the Mission Techniques Committee, the committee approved all the techniques in the mission, happened to be a graduate of Brown University, Bill Tyndall, and he was spectacular. I mean, he could coordinate. In fact, it's sort of like having engineers from all disciplines, like an orchestra, 100-piece orchestra with all the different instruments who'd never played together. Terrible sound. Bill Tyndall got them together. He was a right conductor, and it was a smooth orchestra at the end of the day. So we got approval by the data priority mission techniques for this direct rendezvous ascent, which means we could reduce abort propellant. So I had a bunch of geologists, including Jim Head, as we go on these field trips, they say, hey, you know, we need to have a telephoto lens on the moon so you can get a good picture of distant objects without going to them, or a high resolution picture. Well, I thought it was pretty good. But at that time, mass was critical. I mean, on the lunar module, they had a big program at one point called SWIP, Super Weight Improvement Program, and they literally reduced the number of Band-Aids we had on board because weight was so critical. So I went to the boss and presented the case with a lot of backup and a lot of preparation by a lot of geologists, and then all these simulations on saving abort propellant. And we made a trade, science engineering trade, in that we could give up abort propellant in exchange for a 500 millimeter lens, a telephoto lens. And that one really paid off, and I thought I'd sort of walk you through the result, one of the results of the lens. There it is on the right compared with a normal 60 millimeter lens. It weighed about 3 times as much, still not very much, you know, about 7 or 8 pounds, but still, that was a lot of weight during those days. So there's yours truly, approaching Hadley Rille, and I've got the telephoto lens in my hand because the Rille was a mile away, and it was hardly difficult for a normal 60 millimeter lens to capture the details of the Rille in case there was layering. And the telephoto lens did a great job. And at the same time, there were some pretty spectacular scenes on the moon. On our second EVA, I was up on the side of Hadley Mountain, a little over 5 kilometers from the lunar module and about 1,000 feet above the lunar module. I looked out at this spectacular sight, the plane on the moon, nothing there but a teeny little old lunar module. So Jim Irwin is there, and Jim took a picture with a 60 millimeter lens, and I thought, boy, you know, it's hardly going to show up. So I pulled out my trusty 500 millimeter, sort of like carrying a trusty gun in your holster, and I'll show you a sequence of pictures. There's a picture of the plane from Spur Crater on the side of Hadley Delta Mountain, looking to the north. Craters and boulders and things, pretty cool. But in that picture, if you look closely, way out there, and you could see it very well with the eye, was a lunar module. I thought, man, I want a picture of home, because that was home for us. So I pulled out the trusty 500 and took a picture, and there's a picture with a 500 millimeter lens. And then zooming in on a high-res picture, there was home. And it was pretty comforting to know that it was still there. So we had 3 EVAs, 3 days of excursions going out to explore. One was down to the edge of the Rille, EVA 1. EVA 2 was the side of the mountain where I took that picture. And EVA 3 was the Rille, where I had the 500 millimeter to take a picture of the Rille. In the meantime, because we had some prominent geologists teaching us, we were enabled to put some names on the moon. And and all the documentation now, you can find a place called Head Valley for one each Jim Head who got us to Hadley. Thanks, Jim. Appreciate it.
Let's do it again, Dave.
Go for it. Here's a picture looking north along the Rille. Absolutely spectacular. It's a mile across, 1,000 feet deep. Too steep to go down into it, but not too steep to get some good photos of some of the boulders that are like 20 meters in size, rolling down the side. But a real spectacular show. There's yours truly on the side of the Hadley Delta Mountain. And if you look at the rover in the background, we're working on a slope of 18 degrees, which was rather amazing because we drove up this slope and we didn't realize it. The rover was really great, but once we got there, we found it was very difficult to work in the very soft material on the side of the mountain. Besides that, it was dirty. If you look at my nice white suit, and this is EVA 1, golly, it was really dirty. Now, we got a lot of rocks, and we've been trained to learn these rocks, to find the right ones, and bring it back for our professors. And we learned all the words. We had the breccias, and we had the Mare basalts, and we had the basalts, and you know, Jim Irwin and I, we had about 15 field trips. So we really were proud of our terminology and everything. And then another thing that was sort of unique about Apollo was that the crew were given flexibility in terms of what they picked up and what they explored. We had a plan, but we were given flexibility in doing our geology to select the best samples. But also we were constrained by time, because we only had a certain amount of time in our backpacks for the oxygen and for the cooling water. So we let Mission Control watch that for us. We had little gauges, but we let them watch for it, and they would let us know when we were running out of time so we could get back to the lunar module in time to do the other chores. And after a while, you know, Jim and I really like this geology stuff. After a while, they'd say, come on, you guys, keep moving, keep moving, keep moving. And then finally, at the end of EVA 1, we're driving back, and we saw something and said, hey, Houston, how about a little bit more? No more geology, get back, you got work to do. So we're driving along, and all of a sudden I saw this black rock sitting on the surface all by itself, hardly any dust, pure dark black. And I thought, God dang, I gotta have that dude. So I hit Jim, and we had signals, you know, signals here. So old Jimmy starts talking about the area and geological terms and all that stuff. And I call down to Houston. I say, hey, Houston, I got a problem with my seatbelt. Oh, really? Well, turns out on a moon, when you're driving, it's so bumpy at 16G, you've got to have a seatbelt. And they knew that. And they said, okay, you can stop your seatbelt, but no more geology. I said, oh, Raj. So I stopped, and all of a sudden, my suit got off of the rover, and my suit walked over to that rock, and my tongs stuck themselves in the side for a scale, and my camera took a picture. And then I got back and got in the rover. Took 1 minute and 47 seconds, and Houston didn't know about the rock, and I told him, seatbelt's all fixed. Oh, fine, that's good, press on, you know, so we go back to the limb. And they didn't know that rock was in my pocket until we got back to Houston. So it was a scoriaceous basalt with a lot of vesicles in it, but they gave it a better name. They called it the seatbelt basalt. So anyway, there it was, and it was a beauty. I mean, you can see, look at all the bubbles, those are vesicles. Look at that, that is spectacular. So we moved on. We went up to the side of the mountain to Spur Crater, and one of our objectives was to try to find a crystalline rock called anorthosite, which has a mineral in it called plagioclase. And it was thought at the time, and now confirmed, that the original lunar crust was crystalline, this anorthosite, but it had been covered up by lava, by volcanic material. And nobody had ever found a piece of anorthosite. So my good professors had said, bring back an anorthosite. So we were really keyed to that. And by golly, Spur Crater, we found one. And if you look at the rock on top of the pedestal, next to it is our gnomon, which gives sun angle, scale, and color. And on the right and lower right, you can see a white rock in a pedestal, which the media called the Genesis rock. It was a piece of the original lunar crust. It was 4.2 billion years old, and it was a real treasure. And we're really proud to have been able to find that. And we found some other interesting rocks. You know, and again, boy, we thought we had all the nomenclature down. We really knew these words. And we were going along doing the breccias and the basalts and all that sort of stuff. And finally, I picked up a rock, looked at it, and I thought, you know, we take turns naming them. Because all our professors are listening to us on the ground. I mean, this is the final exam, man. So we take turns. And I say, hey, Jim, it's your turn, Jim. He looked at it, he said, no, Dave. No, Dave. It's your turn, Dave. So he hands it back to me, and I look at it, and I thought, you know, Jim, it looks a little green. And he said, no. So I handed it to him. He lifted his visor, and he says, yeah. He says, it's green. I wonder what that is. So we real quick put it in the bag, and took off. And a little embarrassed. We didn't have any name for this thing. And this is one of the surprises. We got back to Earth, went to the Lunar Receiving Lab to look at all the rocks we brought back with our professors. And as we're going down the various little chambers, why, we got to this one and stopped. And I thought, well, we'll just keep moving on. And pretty soon, Lee Silver, one of our professors, stopped me and said, hey, Dave, don't you want to know what this is? I thought, oh, geez, I get a D on this one, you know. And so he says, you know, we've been looking at that for 3 days. The best we could come up with is a friable green clod. So I thought, well, not too bad. And on the lower right is a blow-up of little green glass beads inside of this rock. It was about 50%, about 1 millimeter green glass beads, about the size of a Coke bottle, and 50% of gray soil indurated or cemented together to make a clod. And it turns out that 40 years later, Professor Alberto Sal at Brown University, using special analysis techniques and being very persistent, found out that in those green glass beads is water. So we found water on the moon, and a Brown University professor verified water on the moon. So that was pretty rewarding too. And we went on to a lot of other interesting rocks. This is a rock that's got some basalt in it and probably some schist and orthosite, but we called it a black and white rock. Another technique that's very valuable in analyzing lunar rocks is called thin sections. Get a very, very thin section of the rock and put it under a microscope, and it's colorful. Look at the lower right. That's a thin section of the black and white rock. People say there's no color in the moon. A lot of color in the moon. Just have to look at it the right way. Then finally, close out, getting ready after our 3 days on the moon. The EVAs we had, number 1 down to what we call Elbow Crater, and number 2 to the side of the mountain to Spur Crater, and then back up to number 3 to the Rille. I took about 400 pictures on the surface. Jim took an equal amount, almost 1,100 pictures total on the surface of the moon in 3 days. So we were really clicking away. We did not have digital cameras. We had film cameras, and they were not automatic. We had to set the f-stop, the time, and the distance manually every time we took a photo, and we had no viewfinder. We had them hooked on our chest. So we had to point it and set everything. But fortunately, NASA anticipated this, and we had great training in that when we first started training, they gave us a Hasselblad camera. Said, go practice it. Practice it. You bring the film back and we'll critique the film. So, you know, we were going to Grumman Aerospace, building the lunar module in Long Island, and we're going out to Downey, California for the command module and whatever. And one of our favorite weekend training exercises was going to the beach and taking a lot of pictures. Anyway, there's close out. Our lunar module Falcon at the end of the 3 days. You see the rover tracks and the footprints. It was a wonderful little machine, I'll tell you. It served as not only our landing machine and our takeoff machine, but home. It's where we slept. It's where we ate. And we set ourselves up on our circadian rhythm so we could operate in maximum performance based on Houston time. So we lived on Houston time. We got about 5 hours sleep a night, good, comfortable sleep, and it was really quite a rewarding machine. So just before we...
In my left hand, I have a feather. In my right hand, a hammer.
That's good. You can hear it.
I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct.
A little science on the moon. No, you got to have a little science on the moon. Anyway, homeward bound, 12 days of exploration, 3 days on the surface, 3 days in orbit, 6 days to and from the moon. We had a lot of experiments to and from the moon too. We had X-ray spectrometer, gamma ray, ultraviolet photos, really a lot to do. 170 pounds of rocks and soil, 1,100 photographs, and a lot of orbital science as well. And down on the lower side is one of the recent pictures of our landing site today, if you will. So if you want to flip that one up, Jay, on the right you see an expanded version of it. And you can see the lunar module, Falcon, sitting here. Here's the rover, where I parked the rover so that they could put the TV on the lunar module for liftoff. Here's our Apollo lunar surface experiments package that we set up manually. And you can see the tracks. You can even see the rover tracks when we went down to the mountain and came back and went out to this side and came back. Pretty spectacular picture. And that's the way it looks today, which is a certain amount of verification that we actually went to the moon. I mean, it's true. It's true. I can only tell you the story, but there's got to be some verification. But anyway, you're welcome to come up and look at that later on, because great picture. It's really fun for me to go to these new photos now. I mean, a lunar reconnaissance orbiter camera is just wonderful. And if you get onto the web, you can find all these photos of all the things we've done on the moon. And it's just a great trip. You can have a really good time. So the results of Apollo, and I think this is pretty important. National prestige. We were in a race with the Soviet Union to see who could put a man on the moon first, which was a demonstration of national capability. And in those days, with communism encroaching on many countries in the world, there was a real contest to show who really was best. And that was Kennedy's objective. We achieved the objectives and established a lot of national prestige. Technological progress, the architecture, the manner in which we go to the moon in terms of launch vehicles and lunar module and command module, operations on the surface, those are progress, and this still can be used today. In fact, if you improve the lunar module with today's technology, structures, materials, propulsion, computers and everything, which a group of grad students did at MIT last year, you can reduce the mass going to the surface by 40%, which means you can put 40% more science on for the same lunar stay, or you can stay longer. So just taking the concept or the architecture of Apollo and applying today's technology, you can double the capability, which is pretty remarkable. Management expertise, one of the real crowns and a jewel of Apollo, was the way the whole program was managed. 400,000 people were managed, and all those pieces had to get to the Cape in time for a launch on time. We were scheduled July 26, 71 at 9:36 in the morning. We launched at 9:36 in the morning on July 26, 71. With all of that mass, 3 big rocket stages, 2 big spacecraft, lunar rover, all the science, everything came together. So it was just an absolute spectacular management capability. Scientific return, we're still learning. Professor Saul just learned about water 40 years after we came home. Formation of the moon. So consensus is now the moon was formed by the impact of a Mars-sized object early onto the Earth, early in the life of the Earth, and all the debris went out into a big orbit or circle, and it accreted into a solid body called the moon. So that's quite a bit of learning from Apollo. Educational stimulus, that's another real benefit from Apollo, because everybody really likes to do these things, and it really gets people interested in STEM. But even more than STEM, even in art. And you know, you see a lot of art related to planetary bodies, related to the moon, and it gets people involved in all that sort of stuff. So a real stimulus to education. And then the spin-offs, the sort of technological things like Tang. Did anybody know about Tang before Apollo? Well, by golly, everybody knows about Tang now. You really get tired of it, let me tell you that. Really. But anyway, Velcro, we didn't invent Velcro, but we sure used a lot of Velcro. Digital computers. Our little computer was the first computer to have a digital autopilot. And I remember the day the MIT guys came in to Houston, had a big meeting, and they said, we're going to show you a digital computer. And everybody said, what? You got to be kidding, that won't work. By golly, it worked. It was the first real use of a digital computer, and I showed you the comparison now with an iPhone. So the spin-offs were significant as well. But everybody has to go home someday. And this is the last picture we took going around the moon. And people say, oh yeah, look at the moon up there. Well, up there is the Earth. Down here is the moon. And the way the timing exists, our view of Earth for the moon was this: the Earth was only crescent illuminated. As you know, the moon goes around the Earth once every month, and the sun stays fixed and the Earth rotates on its axis every 24 hours, but the lighting on the moon changes, and the lighting on the Earth relative to the moon changes as the moon goes around. And depending on your trajectory, why you may have a full Earth on the way home or on the way departure of the moon, or a partial Earth like this. And I like to explain to people that the moon has 4 sides: the near side, the far side, the light side, and the dark side. Because the near side of the moon always faces the Earth. We always see the near side. But as the moon goes around the Earth relative to the sun, the near side is sometimes fully illuminated like a full moon, and the far side is sometimes illuminated, but we can't see the far side. We can only see the near side, which is often dark. And it's a little shiny object out there we call Earthshine. So it's an interesting formation or combination of the two planetary bodies. But for landing on the moon, the key to landing is to have right sun angle when you approach the touchdown, which is like 12 to 14 degrees. And that determines the time of liftoff. So the time of landing, based on the orbital mechanics of the Earth and the moon, sets the time for liftoff to the second. So it's pretty cool stuff. And there's our Earth. Spectacular. You know, it's an amazing gem in the universe. The universe is totally dark except for the stars. And when you're in space, you can see 6 magnitude stars. There's so many stars, it's hard to identify the constellations. But the only color in the universe is the Earth. It's the only color. When you stand on the moon, and if you put your thumb up, you can cover the Earth. It's only that small from the moon. But it's only that small in the universe. And the thing I think we all learn from this perspective, and it was expressed better, I think, by the editor of the Saturday Review, about 2 years after the Apollo program, Congress had a hearing, intellectual and academics and journalists and etc., and they asked him, what do you think was the significance of Apollo? And Norman Cousins, I think, had the best answer. He said, the significance of Apollo was not so much that man put foot on the moon, but that he put eye on the Earth. And I think that's true. Because when you see this, you get an appreciation for the Earth, and hopefully these pictures that come back from Apollo can convey the message, we have to take care of the Earth. It's the only place Earthlings can live. So we better do a better job of taking care of it. And then finally, a word. Space is the only arena of worldwide interest in which the United States can demonstrate at the same time its scientific expertise, technological strength, peaceful intentions, and the openness of a free society. So I would encourage you to encourage space. We need to have the education, but we need to have national leadership in space. And with that, thank you very much. I've enjoyed the discussion, and I'm open to questions. Yeah, questions? Any questions? Okay.
It said you had 170 pounds of rocks and things in soil. How much were you allotted? Was that all you had room for?
Allotted to come back, there was a certain margin, and I really don't recall exactly what the margin was. It was probably around 200 pounds, something like Jim would remember. But the challenge is not just picking up mass of rocks. The challenge is finding the ones that are important scientifically and then documenting them properly and bag them so you don't lose them and bringing them back. So we would weigh them at night inside the lunar module, but we never tried to keep score on mass. What we were trying to do is find the significant samples to bring back for the scientific analysis. Another one?
Okay, I'm a car guy. Why'd you park the car so far from home when you took off? I don't get it.
The what?
Why's the Rover way the hell over there?
Why did you park the car so far away from?
Oh, I parked the Rover, I guess it's about 150, 200 meters, a specific distance, because the television camera was remotely controlled, and it wanted to have a TV picture of the lunar liftoff. In fact, you know, it was the first remotely controlled TV camera from Earth, and there's a 3-second delay, and the guy in mission control who controlled it was absolutely marvelous. In fact, the hammer and the feather, he didn't know about that. The hammer and feather was a secret. And Ed Vindel is his name. We called him Captain Video. And even though he didn't know what I was going to do, and he had a 3-second delay, he anticipated it well enough that he could frame it. And then we got a video of the liftoff, which unfortunately the camera stuck and we didn't get to track the limb going up. But on 17, there's a great video of the limb taking off and going all the way up. Another one. Yeah.
How much of the orbital docking maneuvers and translation did you actively pilot versus what was autopilot?
All of them.
Oh.
Yeah. And I know there's a lot of discussion these days about autonomous rendezvous and whatever, which is pretty good, but we didn't have any, we didn't have computer capability. We did not know how to do it. So all the dockings in Apollo were manual, and the rendezvous were computer-generated maneuvers, but manually controlled. So it was a manual operation, and the humans seemed to do pretty well. You know, that's fortunately, I guess. Huh? Another one. Oh, young man in the corner over there.
Did you have any close calls in space?
Do you have any close calls with anything?
Close calls. Well, yes, everybody has a few close calls. Even engineers have surprises. We had a water leak on the way to the moon, and another part of the teamwork. If you have a water leak in a command module, which we did, in 0G, water doesn't drip. It just bubbles and globs and breaks off from surfaces, and we couldn't find out where it was coming from. And it's a serious problem because the guidance and navigation system is cooled by water glycol. If you lose your water, you lose your guidance. If you lose your guidance, it's hard to find your way home. So when this started leaking about a day out, we were really quite concerned. We got the towels out and, you know, sopping it up, but we couldn't find the leak because of the way water adheres to surfaces. Called down to Houston, of course, and they said, stand by. And I'll tell you two parts of the story. Pretty soon they came up with a procedure, take tool U, tool V, and go behind this panel, behind the environmental control system, and tighten up a couple little screws back there, which we did, and it stopped. At the same time, because the Houston back room, somebody had written up a procedure for doing that. And so they knew, and they passed it up to us. Well, it turns out the guy who had written the procedure about 3 weeks ahead of time, before launch, had the same problem. So he wrote down his problem, his boss checked it, and they put it in the files, and it got to mission control at the right time. But simultaneously, as we were having the problem, this particular tech was driving home from work at the Cape. It was night, and he heard the problem. He stopped his car, he got out and went to a payphone, called up and got through to mission control and said, hey, I wrote a procedure on that 3 weeks ago. And that's the teamwork. And that's what really made everything comfortable for me. I knew there'd always be somebody to solve the problem. We had another water leak in the lunar module on the third morning, which we fixed that one, and we had a little oxygen leak, fixed that one. And then when we came back, our final surprise, on the way down on a parachutes, one of the parachutes failed. So we landed, but the system was designed to land with 2 chutes. There was somebody thinking ahead. So with people on the spot like that and all that support, I was always comfortable that if there's a problem, somebody will figure it out. And the Apollo 13 movie is classical in that way. If you've seen the movie, if you haven't, you should see it. Teamwork, everybody in the family pulls together, and there will be an answer because humans are really pretty smart. Yes?
This whole journey seems so magical. If you had to relive like 5 minutes of it, what was your favorite moment of the entire?
5 minutes.
The favorite 5 minutes in a magical voyage to the moon.
What would I do in 5 minutes?
What was a favorite 5 minutes?
Oh, favorite. Oh, that's a good question. I never had that one before. 5 minutes, huh? Well, landing.
You can be 10 if you'd like.
Yeah, landing's pretty spectacular because you train a lot, and it's very difficult to land on the moon. But everybody was able to do it because of the training we had. That's pretty exciting. And probably the next one was when we first got to the Rille on the first EVA, and I was looking up this canyon that was a mile across, 1,000 feet deep, with beautiful geology that I've been studying for a long time, and it was absolutely marvelous. And one of the benefits of humans on the moon, fortunately to the humans there, the eye is much, much better than the camera. The cameras just cannot capture the scene, but the eye can capture the scene. And one of the things that Jim and I are working on now is how can you improve human performance, and how can you convey this perception to everybody else. And those are probably the 2 highlights, but I showed you the picture of the limb on a plane I took with a 500mm lens. Boy, that was spectacular too. I mean, it was like, wow. You know, the good news is I can see it out there, it's still there, you know, but the challenge is we better get back to it to get home. And dinner. In the back.
Yeah, while walking on the moon, any issues with sweat or itchy noses?
Any issues with sweat or itchy noses?
Hey, that's a good question. It is. You figured out that inside the helmet, you know, you could scratch your nose. You could. But one of the other sides of the challenge that in geology training and field geology, why one of the techniques we have is when you get a dusty rock that's covered with stuff, and if you want to see the minerals and the grains inside the rock, why you spit on it and rub it to clean it off. Couldn't do that on the moon. Couldn't blow the dust off. That was a challenge. Yes, sir.
So with all the technology we have now, what would you do if you got to go back, and what could we do if there was infinite possibilities to go
Well, with the technology today, and as I mentioned, a couple grad students at MIT did a study last year on improving the Apollo system and lunar module with today's technology. And you could basically double the capability or double the time. So it could be really enhanced without trying to build a station or anything else. It's sort of a stepwise process. So we could start by doubling the size, and then as technology improves, it can go longer and do more scientifically.
So what would you do? Science? Yeah.
Huh?
What would you do?
What would I do in terms of?
Going back to...
Man,
where would you go? What would
that's
you
a good question, man, I'll tell you.
And this is
Yeah.
an exam, so...
Yeah, no, that's a good question. Hadley is spectacular, and we know a lot of other areas there that we'd like to go back to. In fact, when we were on the side of Spur Crater, when we found the enormous site, why, I said to Joe Allen, our Capcom in Mission Control, who was really a great guy, a physicist by trade, but he became a geologist too. I was just offhand, I said, hey, Joe, this place is a gold mine. He says, better get moving, the next one has diamonds. So, do you go to the old place or the new place? Well, we've learned so much from orbital observations now, both photography and instruments. Why, boy, there are a lot of places. I mean, Copernicus is really great. Theophilus is great. Tsiolkovsky on the far side is great. I mean, there's just a lot of really great places. And if you said, you know, I have a new system and we can send more crews back, and we can send one every 2 months. That's what Werner von Braun actually wanted to go one a month. And by economies of scale, you start reducing the costs. So I could pick out a half a dozen spectacular sites right now that would be marvelous. So I don't really have a good answer. Wish we could do them all. Yep.
So could you walk us through the emotions of it in terms of like, were you running on adrenaline the whole time, or was there a moment that what you were doing really hit you and you were like, oh my gosh, I'm going to the moon, or even building up to your trip?
Yeah, that's a good question, actually. Well, you know, people ask, were you afraid? I was never afraid. You know, we were aware and concerned when we had problems, but because the system was so good and the people were so good and our training was so good and our background, it was like on launch day, you know, let's go, give me a failure, I'll fix it. You know, you get that attitude, you want to go. Just like an athlete before a game, you know, they want to get in and play the game kind of stuff. On the moon, you know, you have so much to do and there's so many opportunities, you really don't have a chance to reflect very much. But I also like to tell a story. People say, what's it like on the moon? Well, before we went, Jim Irwin and I decided we'd live on the moon like we did on the Earth. And we took our suits off inside the spacecraft, and we pulled the shades down, and we turned the lights on, had supper, and went to bed. I had a little alarm clock. You know, Mission Control would call you, but little alarm clock, woke up, first morning, got up, and we practiced this in a simulator on the Earth. We didn't sleep well on the Earth. We slept really well on the moon. You get up, you open the shade, and you say, Jim, we're on the moon. Way in the back, huh?
A lot of times it's the case that the United States can't come together unless there's like a crisis or emergency. And it seemed like the space race created that kind of feeling so you could get 400,000 people to work together. Do you think that's possible without a crisis? I mean, it seems like you want to hope to kind of recreate that situation somehow, but how could you do it?
Yeah, you know, it'll occur again. And it won't be a crisis necessarily. It's got to be leadership. It's got to be a leader who can make the commitment in the proper way with the support, and that's what leadership is about. You know, got to charge, and I think that will happen. I don't know when it's going to happen, but I think, my guess is, students today will be part of it. And that's the encouraging thing, because students today are really, really smart, what I'm finding. So when I look at some of the geology students over there, they're going to be part of it. May not be an astronaut, but manager or leader or something. There is a role, and I believe it's going to happen again. It being, we'll go back to the moon. I don't know when, but we'll do it. Just because we do those things. We explore. We don't sit around. Humans just, you know, they want to reach out and grab something. So I think it's going to happen. I don't know when. It's not going to be in the next few years. We don't have the capability, but eventually, yeah, I think we'll go do it again. Yeah.
What needs to happen to get a person on Mars, and when do you think that will be possible?
What's happened first?
What was the first part again?
To get a person on Mars, what needs to happen?
What needs to happen to get in? And
The bottom line, I think, on what needs to happen is we have to have some advances in biology for the human, because going to Mars is very, very, very difficult. It's almost a 3-year trip. It takes 9 months to get there, and because of the phasing of the planets Earth and Mars, you got to stay for about 9 months, then you got to take 9 months to get back. Survivability. And technologically, our machines have to last for like 3 years. It's very difficult. And I think a major problem in planning a trip to Mars, in addition to the human situation, is technology advances so fast these days. It's on a pretty steep curve. But when you commit to a project such as the Moon or Mars, you have to stop technology growth. You have to take what you have and put it together and make it work. And in Apollo, our computer, when I went to the Moon in 1971, it was 11 years old technologically. That's pretty old, even then. But today, how long's an iPhone going to last? A couple of years? So the problem that the engineers are going to have is to stop this technology growth, level it out, and then some years later go to Mars with very old technology. And it's going to take a long time to develop the capability to get to Mars, because we have to go back to the Moon first again, learn how to operate. You're not going to send a crew to Mars that hadn't proven themselves on the Moon, because the human factor has to be in there. I mean, you got to have a crew you can rely on that has experience, has demonstrated the capability to operate in a hostile environment like that. Mars is a long, long way off, both physically and physiologically. I think it's going to be a long time. How about young man here?
Has there ever been a sport played on the Moon?
Is what?
Has there ever been a sport played on the Moon?
A sport? Oh, yeah, yeah. Al Shepard hit a golf ball. Purportedly. They said, no, Ed Mitchell says he hit it. Yeah, that was a good swing.
A little competition between astronauts here.
Yeah.
Reportedly.
Maybe a couple more. Yes, sir.
How come we stopped the Apollo missions to the Moon in the first place, so that it's even more difficult for us as a nation to get to the Moon and eventually Mars?
How come we stopped in the Apollo in the first place, which now makes it more difficult to go back and so on?
Yeah, why did we stop Apollo in the first place? Well, there were a number of reasons for that, but I like to say, you know, with technology growth and technology drift, you have to stop sometime. Overall, in a great scheme of things, we couldn't keep running Apollo because it was old stuff. At the same time, we ran out of money. We had been to the Moon and achieved Kennedy's objective, and all the senses and all the trends were, you got to turn it off. It's too bad. I'd like to go forever. We couldn't keep going forever. But I like to say, as an analogy, Columbus has just returned, and the Moon, or the Earth isn't flat after all, but Cabot and Magellan have not yet made their voyages, and Captain Cook hadn't even been born. So we're going to have it happen again later on with a better system and better capabilities. But at some point, we had to stop Apollo. We couldn't keep going forever. One more. Yes, sir, in the back.
The photo on the right, when was that taken?
This year. This year.
This big one?
Yeah.
When was it taken? This
When
year.
was it taken?
This year.
It was this
year.
This year?
Yeah.
Yeah, this year.
Yeah. The spacecraft is in orbit right now.
How did the one you landed on get back on the Moon?
No.
Say that again?
Explain how the LEM actually,
This- oh,
it left the bar.
The descent stage and ascent
Yeah.
stage.
This is the descent stage, and the ascent stage
Oh, okay, you're
uses
right.
the descent stage for launch. And sort of, as a closing comment,
Separated.
huh?
It's separated.
Exactly.
Yeah, they separate.
Okay.
And
So the part that actually docked with the,
yeah, with the command module in lunar orbit.
where did that end up going? Just space junk?
No, actually they took the ascent stage and they impacted it on the Moon at a specific place to get a response seismically, and now it's a fresh crater if we can get back to it. It's no longer useful. And I also like to say, you know, Jim Irwin and I, we felt pretty good about all this sort of stuff, and we're getting ready for launch, and you know, here we are on the moon, 240,000 miles away from anybody, and we have this spaceship, and we do the countdown and all that sort of stuff. Well, at Cape Kennedy, the firing room at Cape Kennedy has 240 consoles. To get the Saturn off, we had one with 2 guys. So we did the whole launch without 400,000 people, except they were watching us closely. Anyway, thank you for your attention. Good luck to everybody. Good.